Hello, and thank you for joining us today. We're going to be waiting a couple more minutes as we have people that are still registering and coming online. So let's just wait a couple more minutes. Hello, and thank you for joining us today. While we wait for other people to join, I would like to invite you to sign up at ibm.biz/datagurus. We are doing a lot of webinars and meetups and hands-on labs, helping people become more proficient with Hadoop and Spark open source projects mainly. So if you want to stay connected and you want to be invited to future learning opportunities, you can sign up here and get an email inviting you when we have a new engagement scheduled, or you can follow us on Twitter, data_gurus, or on YouTube. We're posting all the webinars that we are hosting and that are being recorded. I would also like to direct you to a handout that I've made available in the control panel. If you download it, you're going to find information about future webinars that we have in the next couple of weeks. And so that if you want to register for those, you're welcome to do so. So today our topic is streaming data analytics with Spark Streaming, and our presenter is one of our engineers, expert in Spark Streaming, Suresh Madlapudi. And Suresh, feel free to get started now.
Right. Thank you, Anna. Okay, can you see my screen?
Yes.
Hello. Welcome. My name is Suresh Matlapudi. I'm a solution engineer with IBM Open Source Analytics Group. So my day-to-day job involves using Apache Spark. So I'm very excited to share one of the popular module for Apache Spark, which is a streaming module. So that is what we are going to talk about today. So this topic is intended for audiences with some familiarity or working experience with Apache Spark core, because streaming module is based on Apache Spark core. It will be helpful to have that background. Also, we are going to focus more on the internals of Spark streaming module. I'm not going to go into any use cases for streaming applications, or I'm not going to compare Apache Spark streaming with other streaming frameworks out there. There is already good material available and presented by some of our colleagues covering these topics, so you can actually get that information from there. This topic, I want to focus more on the Spark streaming internals so that you will get a good understanding of this important module. So this is the high-level agenda for my talk today. We'll go over the overview, followed by architecture and execution model for streaming. Then we'll talk about streaming input and output. Then we'll briefly talk about the streaming operations and required API calls. Then I'm going to share my experiences with the fault tolerance and reliability, which is very important for any streaming applications. And also at the end, we'll talk about some of the performance considerations you need to take care. Okay. I'm hoping I will cover these topics in first 30 minutes. Then we will go into the code. If I have sufficient time, I can show you a live example of how a simple streaming application. So let's get started. What is Apache Spark streaming? What is the Spark streaming? Spark streaming provides a way to consume and process continuous stream of input data. Right. So it was, as I mentioned earlier, it was built on top of Spark Core API. So you might already know that Spark Core API is designed for batch processing, and RDDs, or resilient distributed data sets, are fundamental data structures in Spark Core. So Spark Streaming API is similar to Spark Core API. Okay, so pay attention to streaming and Spark Core APIs here. The advantage with that is if you have used Spark for batch processing, it is easy to learn Spark streaming, but you need to understand its execution model for Spark streaming. Just like Spark Core, Spark streaming also supports multiple programming languages. You have Scala, Java, and Python APIs. Depending on your programming language background, you can use them to write your streaming applications. So Spark streaming defines a new abstraction, which is called discretized streaming, or D-streams. So just like Spark Core uses RDDs, Spark streaming uses D-streams. Okay. A D-stream represents a sequence of RDDs where each RDD is a collection of records that accumulated with a specific time interval. So there is also a new interface called structured streaming that was introduced with Spark 2.0. It provides or it brings some improvements over these streams. So some of these improvements are like reducing programming differences between Spark streaming and Spark Core, other Spark modules, and also improving state maintenance. So it is still in early stages, and I'm not going to talk about it. We will focus on its execution model and D-stream based API. But if you are interested in structured streaming, I highly recommend to attend our webinar scheduled on February 15th, which is about Spark streaming, Spark structured streaming. So let's talk about streaming architecture. So as I mentioned earlier, Spark streaming is built on top of Spark Core. So the Spark streaming uses a micro batch architecture and operates on time interval. So what I mean by time interval is when you are reading a continuous input data or input records, and if you had to batch them, you can either use, you can do that either by size or you can do it by time interval. So Spark streaming uses the time interval in this case. So if you are familiar with Spark batch architecture, you know that the first step in Spark program is to get the data into the cluster for parallel processing. So usually you do that either by reading from a distributed file system like HDFS, where data is already distributed for parallel processing, or by reading a sequential data in a driver program and calling Spark context parallelize method to create a distributed data set which can be operated on in parallel. So in micro batch based streaming architecture, we need to be able to do this on a continuous basis. So that is reading the input records from streaming source, batch them and distribute them across the cluster if required, and then process each of those batches. Okay. So let's talk about this in detail. So recall that distributed streams, these streams is the basic abstraction provided by Spark Streaming. So it represents a continuous stream of data. So most of the input D streams, except like file stream and some APIs, most of the input streams are associated with a receiver object. So a receiver object, nothing but, right, it receives the input data from source and stores it in Spark's memory for processing. So this receiver is executed in a thread in one of the worker node. So that is on one of the executors. Yeah. So if you are familiar with Spark core architecture, you have a driver program and you also have more than one executors usually to process the actual data. So that is a very high level architecture of Spark core. Right? Take an example of input D stream configured with one batch interval. We talked about Spark uses time interval to batch the input records for the micro batching. So let's take an example of that with 1 second batch interval. So at the beginning of each second, a batch is created. So any data received during this interval gets added to that batch. So let's call this as batch 1 here. So each batch is organized into multiple blocks so that they can be operated on in parallel. Okay. So what I mean by that is within 1 second, if you have a single batch of records, we cannot parallelize that. So dividing that batch into multiple parts makes it easy for parallel processing, right? So we call that as blocks. So pay close attention to batch and blocks. If you understand these two differences, then right, you will understand when it comes to the Spark streaming tuning, that understanding is very important. So number of blocks created within a batch depends on a variable configuration, which is called block interval. By default, the value of it is 200 milliseconds. Okay. So going back to our example of a batch interval of 1 second with a block interval of 200 milliseconds, each batch will have 5 blocks. That's how these two variables constitutes to create the blocks. So at the end of each batch interval, an RDD is available for processing, where each block in the batch constitutes a partition. You remember Spark processing, each executor task works on a partition. Okay, so in case of streaming application, each block will constitute that partition. Okay, so depending on once this is done, at the end of the batch interval, depending on the application process logics, so jobs are created and queued to process these RDDs. So we'll talk more about this in next slide. Okay. So for example, if you have 3 worker nodes in our cluster, with each worker node has 2 cores. Okay. So this gives us a total of 6 cores. So assuming that we are working with a input stream which requires a receiver, so that takes one core, right? So Spark Streaming requires that core on an ongoing basis to run the receivers. And removing one core, we will have 5 cores which can be used to run the tasks to process the RDD partitions in parallel, as shown in this diagram here. Once data is processed, the output of is the batch processed batch data. So these steps repeat for each batch interval and for each batch of data, and this is a continuous process, right? So because we are dealing with streaming data, Spark Streaming has the ability to remember the previous RDDs, which allows windowed calculations. Okay? So based on whatever I mentioned so far, the processing is limited to within a batch of data, right? But sometimes that is not sufficient. So you may have some calculations where you need data from the previous batches, right? I mean, not infinite way, but right to certain extent. So that is where these windowed calculations come into the picture. So these calculations are where you need data from previous few batches. So we'll also talk about this in details. So at this point, we covered how the micro batches are created. So let's talk about the Spark jobs which process these batches. Right. Earlier, I mentioned that Spark job creation depends on the application process logic. So let's look a bit closer on the way jobs are created in the Spark stream. Okay. So when you start a streaming application, it starts with a DAG or directed acyclic graph that represents application processing. Okay. So which is on the left-hand side of this diagram. So for each interval, a RDD graph is created. It is basically the same as DAG, but with RDDs created for that batch as input. So just like Spark Core API, streaming API comprises of transformations and actions. Remember, in Spark batch processing, only the actions creates the jobs, right? So in our example here, we have 3 actions. So that is the reason each batch in our example executes 3 jobs to process that batch. So the RDD graph goes through the same process as in Spark batch, where a stage is distributed over a number of worker nodes based on number of blocks created for that RDD. Okay, so this covers the overall architecture and execution model. Let's talk about input and output for Spark streaming. So Spark streaming may depend on Spark execution engine to do the processing, but it needs interfaces to outside world to read the data in and give the output to outside world. So currently there are several data structures that are supported as mentioned in the slide. In case of sources like a file streaming, Spark streaming can read it directly. There is no need for receivers. So what I mean by that is, if you are reading a HDFS files created in a particular directory as an input source, those files are already available in HDFS, and most of you know that HDFS uses blocks to organize the files. So that means data is already partitioned for you. There is no point in reading all the data in one receiver and then distributing to the cluster where the data is already distributed in the cluster. So the ideal thing to do there is each Spark executor can read the data from individual nodes of HDFS, right? For other data sources, an execution thread must be allocated for each instance of them to run the receiver. We talked about this. Typically, these are sources like Kafka, Flume, Kinesis. These receiver libraries are available through external utility classes. So you may have to do some additional linkage with these jar files. Right? Also, when you talking about Kafka, which seems to be the most popular input streaming source in combination with Spark Stream, there are two different APIs. One API is receiver-based approach, which uses a single receiver or more than one receiver to read the data from Spark, read the data from Kafka and distribute it to the Spark cluster. Whereas the second API, which uses a direct approach, which actually doesn't use any receiver, because the data is already partitioned in Kafka, executors can read directly from individual partitions. The second API, which is a direct-based approach, should scale better than receiver reading it and distributing it. Okay, so I'll show you example code with a direct reading-based approach. Also, the output targets are supported through Spark with few functions already defined for specific ones. So as you can see in this slide, save as text files, save as object files, or save as Hadoop files. So these are some of the output operations. Okay. In addition to that, there is also a API call which is for each RDD, which gives you more flexibility on how you want to output your processed data, right? So let's talk about Spark Streaming API, which includes the dstream classes. As I mentioned, Spark Streaming adds another layer on top of RDDs. So there are different classes you need to use for Spark Streaming. Okay. If you can read some of the class names on the on the right hand side, you can see that these classes have dstream names in their names, right? And also, depending on the programming language you are going to use, these classes, you need to select the right package for those classes. Okay, so it's going to be, there are too many combinations of these, so I'm not going to talk about individual classes here. So the best place for you to get the information on these classes is to refer Spark API documentation, depending on the specific language API you are planning to use. Okay, but note that dstreams are not RDDs. Even though they are built on top of RDD, the API support may vary. What I mean by that is, if you are used to use some RDD functions, you may not have that same support with the dstream classes. Okay, so be aware of that. So at high level, these are the operations, group of operations for Spark Streaming. Okay. So the first set of operations here, like map, flat map, filter, reduce. So these are the transformation operations. Very straightforward. You will see most they are similar to your Spark Core API. The only thing is the input, you have to deal with these RDD instead of individual records. Okay. There is also a Windows operations which I have mentioned earlier. We'll talk about that more in the next slide. But right, we have options like window, you have count by window, and reduce by window. Okay. Finally, we have output operations. We talked about it earlier. One thing I'm going to mention one more time again is for each RDD. For example, the output operations you see here, you can only see function calls for saving the output as files. What if you want to write to some, let's say, key value store, or what if you want to write to a database or some data store, which is not here? That is where your Spark streaming for each RDD function gives you that flexibility. Once you are in this function, you have access to the RDD, and with that RDD, you can extract individual records and do whatever the output you need to do, whether it is a data store or it is some other external output you need to send the data to. So let's talk about windowing capabilities. So windowing in Spark Streaming is done using two parameters. First one is a window length. Second one is a sliding interval. Okay. So both these parameters must be multiples of batch interval. So why do we need two different variables to do that? Okay. So, but if you take an example, it will be very clear. For example, consider an input D stream with 1 second batch interval. So for every second there is a batch created and there is a jobs created for that, right? But what if we need to do some calculation at every 2 seconds instead of 1 second, right? Every 2 seconds you want to find, let's say, last 3 seconds of data. You want to find something from last 3 seconds of the data, or maybe you just want to count them, right? So that is where you need two different variables. Okay. So in this example, the window length is going to be 3 seconds because you want to reach out to the last 3 batches, and the sliding interval is 2 seconds because you want to do this operation every 2 seconds. Okay. These windows are specific to dstream operation, and they're also stateful transformations. So we need checkpointing. We must enable checkpointing for that. Okay, so we'll talk about checkpointing in our next topic, which is fault tolerance. The most important difference you will realize when you are shifting from developing batch application to streaming application is the streaming applications must operate 24/7. So hence they must be resilient to failures unrelated to the failures unrelated to application logic. Obviously, if your application logic has issues and your streaming application is failing because of that, you need to fix that logic, right? But other than that, any other issues like in cluster computing, it's very common to have your nodes going down or maybe your containers crashing, but your streaming application must recover from those to process your jobs normally. Okay, so this should be your number one technical requirement. You should add it to your streaming application design. Okay. So there are different ways you can achieve that I mean, there are different areas you have to take care when you're developing with Spark streaming application. By default, the data received by a Spark streaming application is replicated with the factor of 2. Okay. Spark core or Spark batch doesn't replicate the data, as you may recall. It depends on RDD's lineage to recreate that RDDs when there is a failure, right? But whereas in the streaming, you are getting a continuous data from an external source, right? So once you read after you read the data once, you cannot go back and read that same set of data again. So that's the reason streaming uses a replication to give some resiliency there. And also,
there's a question. The question
sure.
is check pointing related to name node edit logs. Name node, I'm guessing there's a typo.
No, this checkpoint is totally different than your name node checkpointing. So the name node related things, they are related to HDFS, right? Hadoop distributed file system. Spark, on the other hand, is an execution framework. It can use HDFS as one of the file system, but it can also run without HDFS, right? But the Spark streaming checkpointing is, I'm going to talk about this now, so which gives you some information on that. Okay. So Spark streaming needs to checkpoint enough information to fault-tolerant storage systems like HDFS, so that sorry, I was behind that slide. So that it can recover from failures, right? Checkpointing is very common for recovering from the failures. It's nothing but, right, you take the information of the state of your application, and you at frequent intervals, you store it outside the memory, so that when your application restarts, you read from that to build the state to that point of failure, right? So when it comes to Spark streaming, there are two types of data that needs to be checkpointed. First one is your metadata, and second one is your RDD checkpointing, RDD data checkpointing. Okay. So metadata checkpointing is primarily needed for recovery of the driver failures, whereas your data or RDD checkpointing is necessary if you are using stateful transformations like Windows, which I mentioned earlier. Okay. So let's talk about the driver program failures. This is one very common thing you are going to experience if you deploy a Spark streaming application in a cluster mode. Okay. So as you recall, there is one driver program for Spark, and there are multiple executors, right? So the driver program is responsible for the overall orchestration of execution of the tasks, right? So what will happen if your driver program crashes, or maybe the node running the driver program crashes? So you need to have an ability of restarting the driver program automatically, and also the driver program should recover that state from the point of failure to the current state, right? So that is where the checkpointing comes into the picture. If a node running a driver program for Spark streaming application fails, you need to restart it automatically. So this again depends on what type of cluster you are using. For example, if you are using Hadoop, Yarn has a setting of restarting the application multiple times automatically. Okay. So I think the default value is 3 times. If a driver program goes down, it will restart it automatically. Okay. One of the example I have is with this checkpointing. So it will be a little bit clear for you when we go through the code. I hope I'll have sufficient time at the end to go in details. The last type of fault tolerance you need to consider is the back pressure. Okay, so this is purely related to the capacity of your Spark streaming applications to handle the volume of input data. Right. The basic need to keep your Spark streaming application stable is to have a sufficient cluster resources to process data that is being received by your receivers. Right. So are there any guidelines for this? Usually, right, it takes a monitoring and few iterations during your deployment to estimate the required cluster resources. Like these resources are like number of executors and what is the memory for each executors and number of cores for that, right? So even with that, let's say you are taking care of that, right? So you may have occasional spikes in the input data, right? So consider a scenario where receiver is reading the data faster than the cluster resources can process the data, right? So this leads to too many batches queued up for processing, and if this continues for a very long time, your entire Spark streaming application may crash, right? So to avoid that, Spark includes a few settings. Use the two parameter settings mentioned in the slide. One is the back pressure enable, and second one is the receiver's max rate to avoid these occasional spike scenarios, right? But end of the day, you need to give the enough cluster resources to your Spark streaming application to handle your average volume, input volume of data. Not only input volume of data, and also the what type of processing you are doing to on top of input and to get the output. So that covers the fault tolerance topic. Finally, let's talk about performance recommendations. Okay. So as I mentioned, right, when it comes to streaming, it's all about making sure that the Spark engine can execute the jobs as fast or faster as they are created, right? So if Spark cannot keep up, the latency must increase. So this also impacts the level of parallelism, since more parallelism increases the number of tasks. Okay, so you may ask, okay, how do I increase the latency, right? So the batch interval is the latency here. So from 1 second, you may increase that to 2 seconds. Obviously, that requires more memory to that streaming application, but you will have fewer batches to process. That means fewer jobs for Spark streaming application to invoke less number of jobs, right? So in general, right, we have to weigh the cost of starting the jobs with the execution time of each batch. The lower the latency, if latency is low, the higher the overhead. Okay, so if you are using, let's say, maybe sub-second batch interval, that requires a Spark streaming application to create jobs within very short duration of time, and obviously there is some overhead on Spark side to delegate these jobs to the executors, right? So you have to consider all those scenarios and come up with a suitable batch interval. Usually people leave the block interval to default 200 milliseconds, but you can also use that to optimize your application. Okay. So finally, you also need to consider that, okay, Spark is based on JVM. Okay. So what that means is, right, you need to face same performance considerations as any other Java programs. Okay. So the most common one is the efficiency of garbage collection, right? The notorious garbage collection process, right? So you have to closely monitor that Spark streaming application, see how that is impacting. This is especially important if you, let's say, if you have a requirement for stringent sub-second latency for let's say real-time application. Okay, so then you should look for a streaming framework which is not based on Java. You have to look for maybe a streaming framework with a native execution, like IBM Streaming, IBM Streams, which is based on developed in C++, which will not have this overhead, right? But for most of the analytical streaming applications, the micro batching architecture will do the job for you end of the day, right? It's just that you have to initially closely monitor it, make sure that you optimize the streaming application so that it can run on a continuous basis. So that covers the theory behind Spark streaming. Just to quickly recap, we talked about the execution model of micro-batch architecture. We also talked about sources, input sources, and output operations. Also briefly touched upon the Spark streaming, followed by the fault tolerance and performance considerations. Okay. With that, I want to show some code demonstration. I think we have still 20 minutes, so let me try to cover two different applications. The first application is with a file streaming, a simple application which reads the data from a HDFS input directory and does very trivial operations on that, and then output to again HDFS directory. Okay. The second one is Spark streaming application which reads the data from a Kafka input source and output to HDFS file system.
Suresh, there's another question.
Sure.
Without JVM involved on the execution side, what is the other process that you mentioned?
I was talking about totally a different streaming framework. So IBM has a streaming product which we call it IBM Streams. Okay, so it is serving multiple time critical streaming applications, especially banks and risk related applications. So if you have a similar requirement with sub-second latency, you should explore products like that instead of trying to use a JVM based micro batch architecture.
Okay.
Okay. So what I have here is I have IBM Bluemix account, and I created a small Hadoop cluster which includes a Spark. So let me try to do a live coding here. Hope it will work. So this is my entry node. I'm just logging into my entry node so that I can use a Spark shell to run my streaming application. I'm trying to create three windows here. All right, fantastic. All right, so what I have done earlier is I downloaded a small CSV file, which Anna, can you see my screen? Can you read the font, or do I need to increase the font so that everyone can read the code?
I think it looks fine.
All right, great. So as you can see here, this is a very simple file, comma separated values. So this is actually, I think for 2010, all the Powerball or winning lottery ticket numbers, right? We're not going to use that data much, but right, I just want to show a simple example. What I'm going to do is I'm going to write a small script which takes this file, renames it, uploads to a particular HDFS folder. So that simulates my input streaming data files on HDFS. And at the same time, I'm going to start a streaming application using Spark shell to read that input file from that folder, or maybe do some filtering, and then store that information back to another HDFS folder. Okay, so that is what I'm trying to do here. So first, let me try to show my HDFS folders. I'm launching my Ambari console. From there, I can show you the HDFS. So I logged in. You might have noticed I logged in using a application ID called app ADM. So this will be my home folder on HDFS. So let me go back to the terminal, create a folder, the demo, and two subfolders under that. One is in to copy my input files from my script, and second folder for storing the output from my Spark streaming job. Okay. So meanwhile, let me start a Spark shell with cluster mode. So I'm running a Spark application in a cluster mode. That's where this master yarn comes into picture, and I'm also doing it using two executors. I'm giving a name called streaming demo. Okay. All right, so it is going to take maybe a few more seconds to my Spark shell to become ready. So meanwhile, let me work on my script to copy these files. Trying to for renaming the files, I cannot copy the same file again and again. So I want to attach a sequence number to the file so that I can copy that. Let me test this. Okay, so that is working. So let's use the same thing. Just put Hadoop first. The place I'm going to copy these files, as I mentioned, demo and in, right? And I'm going to rename that as ifile dot sequence. Okay, and also I'm going to do this for not every second, maybe every five seconds. Okay, so this should copy my files to HDFS. Okay, we need to have something to indicate it is working. Okay. All right, so if I go back to my HDFS folder, demo, input, So you can see right every 5 seconds you will see one input file. So this basically simulates my input stream. So let me go back to my Spark shell where okay, fantastic. I have my Spark shell created. The Spark shell by default gives you a Spark context and also creates a SQL context, right? But it doesn't give you a streaming context, right? So we need to create at high level, these are the steps we need to do. So you need to create a Spark streaming context with a certain batch interval, and then depending on the source you are going to use, you need to read that files and then do operations and do the go for the output operation. Okay, so in our case, I'm using the input file stream. So the first step here is you need to import some libraries. As I mentioned, depending on the receiver you are using, you have to libraries you are using, you have to link some of the libraries which are part of Spark streaming. Okay. So the first step is, as I mentioned, right, creating a streaming context using the Spark context, right? So by convention, this is usually named as SSC, that is the Spark streaming context, just like SC stands for your Spark context, right? So in our case, let's make this as maybe 20 seconds, right? So right now you have the streaming context. The next step is reading the input files. Yeah. So my streaming is a file source, so I'm naming it as a file streaming. And this is where we are going to give the input folder. All right, so let me refer that API call. So the required call here is not text file streaming, it's text file stream, not streams. Okay. So at this point, we have the file streaming, and now we can do some operations on that. Maybe do a filter, right? Taking the entire record and look for, so let's say in our case, remember there is a date field in that. I want to keep only the records from August month, right? That's why I'm doing that filter, and then I can do a save as text files. So we just have to give the output folder here. So there is nothing there because we haven't started this yet. So I'm giving a prefix for my files here. Okay, so that builds my DAG, as I mentioned earlier. All we need to do now is we just have to start our streaming context. Okay, so at this point we have this streaming batch is run every 20 seconds here. Let's try to refresh. So as you can see, it's picking up from the input folders, right? And every 20 seconds, you will get one folder created with the prefix I have given, August hyphen, and the data is stored within that folder. Okay. So that I think we are running out of the time. I want to keep at least a couple of minutes for other any questions. So this is the sample of streaming file streaming source. Okay. The second application I want to show is the Kafka based reader. Okay. It follows the similar steps. First, we need to create a streaming context, and then using Kafka util, you are going to create a direct stream. Okay. So once you have that, the rest of the operations follow a similar pattern like any other source. Okay. So the API calls, depending on your receiver, will differ. Okay. Also, if you notice this, I'm doing the checkpointing here. Okay. So the usual format of the code here is you wrap all your Spark application building logic into a function. As you can see here, this is my function to create a streaming context, which includes creating the Spark streaming context, invoking the receiver, adding all the rest of the steps, and finally I do a checkpointing to a particular HDFS output folder in my case, and then we just have to return that stream. Okay. And in your main application, this is how you need to create or use the create streaming context application. Okay, so based on for example, if you what this call does is the get or create is if you are starting a new application, okay, it goes to that HDFS folder, looks for any checkpointing data. If the checkpointing data is not there, it assumes that this is a fresh new application, right? So it starts from that point of time. Otherwise, if it sees a checkpointing data out there, it will read that checkpoint data, which is nothing but a state of your application, and try to build your application from that point of time. Okay, so that is why you have to, by using checkpointing, which you need to use in most production applications. This is the usual format you have to follow for your coding. Okay, once that is done, just like you need to start your streaming application, and you wait for the terminations. Okay, I haven't done the wait for termination because I was using Spark Shell earlier, but in your production applications, this is how you do it. And also, depending on what build tool you are using, you have to use a different. There are different dependencies you have to link. So in my case, I'm using Maven here. Apart from Spark core, I'm using a streaming module. I'm also using Spark streaming Kafka, right? And also there's a dependency on Kafka library also. I'm using version 1.6. So depending on your version and receiver you are using, look for the required dependencies and build your prom file or other dependency files accordingly. So I hope it is useful to you. Sorry, I have to rush in the rush for the last example, but I hope it is useful for you. I'm giving control back to Anna now. Thank you all.
Are there any questions? There are no questions right now. Are there any questions before we end the webinar? Yes, we have a question from Guru Prasad. I unmuted your line. Hello? So I guess not. Thank you
Okay.
so much for joining us today. The session has been recorded, and you will receive an email tomorrow with the link to the webinar. And I would like to invite you again to download the handout that's available on your control panel so that you can see what future webinars we have in the next couple of weeks. Thank you so much.